Hello! So in this video we're going to be talking about this thing called the logarithm and complex exponentials. Alright, so let's just remind ourselves of what a logarithm actually is, kind of set the scene again. So let's say we have 2, okay, and we raise it to the power of 3. Well, the 3 tells us how many 2's we just multiplied together, fairly obviously. This is going to be equal to 8, so it's 2 times 2 times 2. Okay, you're with me so far? Well, what have we got? We've got the 2, we call that the base. Okay, so we've got special names for all of these 3 parts going on. The 2 is the base. Then we raise it. The thing which we raise it to is known as the power, sometimes known as the indice. It's the same thing, okay, or the exponent. And then this is going to be equal. The thing on the right-hand side is just equal to the number. So we call the 8 in this case the number. So the base is 2, the power is 3, and the number is 8. Well, the idea is that we can rewrite this expression in terms of any 3 parts. So at the moment it's written in terms of 8. It's written in terms of the number. The number is the subject of the formula, if you like. Well, we can easily make 2 the subject of the formula. So we can make the base the subject of the formula quite easily. How do we do that? We'll take the cubed root of both sides. So if we take the cubed root of 8, then we get 2 again. Okay, so we can now rewrite this to make... So this is written with the number as the subject of the formula. Now we can rewrite it as the base as the subject of the formula. Well, what happens if I want to write the power as the subject of the formula? Well, I can do that, but I have to use this function. And this function is known as a logarithm function. Okay, so I'd write it as log to the base, which in this case is 2, of the number, which is 8, and that will give me the power out. So in other words, the logarithm is just a special way of writing power as the subject of the formula. Well, there's a special type of logarithm called the natural logarithm, and that's just where the base is e. So say, for example, if we have e to the power of 3, okay, whatever that may be equal to, let's call it a, it's just some number, all right? I can rewrite the power, which is 3, as the subject of the formula, just by taking what's known as the natural logarithm. So we've got log to the base, which is e, of a, okay? Well, log to the base e, because it's kind of, e comes up everywhere in kind of nature and stuff, and it's kind of natural. Okay, so it's known as the natural logarithm of a. Okay, so that's a special case. Well, there's a few kind of situations that we can look at now, right? So if we can have, I want to basically say, right, what happens if I raise e to this natural logarithm now? So what happens if I raise e to the natural logarithm of, let's say, x? Okay, well, what's that going to be equal to? Well, let's say it's equal to some number, and let's say it's equal to y. That's our number, all right? And so now if I just rearrange this to make the power the subject of the formula, so in other words, natural logarithm of x is equal to log to the base e of y. Well, log to the base e is our special logarithm, which is our natural logarithm, so it's going to be the natural logarithm of y. Well, then I can just read off exactly, because I'm taking the natural logarithm of effectively the same thing. Okay, because the natural logarithm of x is equal to the natural logarithm of y, so therefore x has to be equal to y. Yeah? So in other words, now let's put it into context. So therefore, I've got e to the natural logarithm of x is equal to y. So e to the natural logarithm of x is equal to y. Well, I've just worked out down here that x is equal to y. So therefore, that's equal to x. So in other words, the e and the natural logarithm kind of cancel each other out. Okay, and I'm just left with x. All right? Well, I can look at it from the other point of view as well. So in other words, here I raised e to the natural logarithm of x. What happens if I take the natural logarithm of e raised to the power of y? E to the power of x. Let's stick with our notation. E to the power of x. I'm taking the natural logarithm now of e to the power of x. Well, let's again say that's equal to y. So it's equal to some number. I'm not sure what it is. Actually, let's call it b. Okay, because it may not be the same. It is, but we don't know that yet. All right. So, same kind of thing. Okay, I'm saying that natural logarithm of e to the x is equal to b. Well, like I said up here, I said the way to kind of think about this is log to the base 2 of 8. So what do I have to raise 2 to get 8? And the answer is 3. So let's ask the same question down here. What do I have to raise e to? Because this is effectively the logarithm of e. Yeah, natural logarithm of e. So e raised to what gives you e to the x? Well, fairly obviously that's going to be x. Yeah, that's equal to x. Right. So now what I can say is that e to the natural logarithm of x is equal to x, but also the natural logarithm of e to the x is also equal to x. So these things are equivalent, okay, if x is a real number. So now what I want to look at is what happens if we've got complex numbers going on. So if it's a real number, if x is just some number, real number, then that's fine, this works. But what happens if it's not a real number? Okay, so let's suppose it's a complex number. So in other words, I want to say, okay, e to the logarithm of z, so z is now a complex number, z is now a complex number. I'm trying to and see if this case still holds, if this is still true. So e to the log z is equal to the log of e to the z. Okay, and notice now that I've swapped back to my logarithm notation. The reason for that is because this is just log to any base. Okay, so as long as these two bases are the same, it's fine. It's the same kind of idea here. All right. Yeah, it'll come clear why I'm using this at the moment. I'm using it's kind of very small point. Don't worry too much about it. Okay, so what I'm going to do is I'm first of all going to look at this left-hand side. Okay, then what I'm going to do is using my results for my left-hand side, I'm going to look at my right-hand side and see if these two things are equal to each other. So that's the idea. So let's look at the left-hand side first of all. So in other words, I want e to the logarithm of z is equal to z. Okay, well what I'm going to do is I'm going to write z in my modulus argument notation, or Euler form, r e to the I theta. Yeah, hopefully you've seen that before. Right, so in other words, what this is saying is if I substitute z for r e to the I theta in here, I should get the same thing out. So e log of, actually no, first of all, I'm just going to, just for simplicity, I'm going to write logarithm of z, which is r e to the I theta. R e to the I theta. All right, and then I can separate this up. So I can separate this up just using my logarithm laws. So I've got logarithm of two things multiplied together. So that's the same as the logarithm of the two things added together. So logarithm of the first thing added together, logarithm of r, plus the logarithm of e to the I theta. That's just logarithm laws, and that comes from laws of indices, the equivalent one where you have to add powers together, and it's just the same as multiplying the bases together. Okay, well look, this is, are you happy that this is real? Okay, this is logarithm of r, which is just a real number. Okay, so this is a real function. Remember that logarithm is just a function, so this is a real function of z. And this is, if I then bring this I down, again by logarithm laws, yeah, I bring this I down, just put it out the front. That's just logarithm laws. Okay, well this is I times another function of z. Okay, so in other words, I've got a real part, and I've also got an imaginary part. Okay, and that kind of makes sense because I'm taking the logarithm of a complex number. Okay, so this is effectively what I want. Okay, I want to basically say, well, okay, the logarithm of z, I want to look at the logarithm of z first of all. I want to show that that is equal to a real part plus an imaginary part, imaginary functions. Okay, where u and v are just functions. Okay, so I've set up here that I want to raise e to this thing, e to this logarithm of z, okay, and I want to get this thing back. So let's see if that happens. So e to the logarithm of z, which I've said logarithm of z is just going to be equal to this thing here, and I'm going to drop the dependence on z. Now you're happy that u is just a function and v is a function. They're both dependent on z, so I'm just going to drop the dependence on z. So e to the u plus iv, just for convenience. Okay. Well, that's going to be equal just again by exponent laws or laws of indices. So this is e to the u times e to the iv. Okay, and I want that. I've said that that is equal to z. Okay, is equal to r e to the I theta. Right. So let's actually look what's going on here. I can just compare the two things together. So this is a real part. This is an imaginary part because it involves I. This is a real part, and this is an imaginary part because it involves I. So I can now say that e to the u equals r. Okay, and I can also say that e to the iv equals e to the I theta. Right, so what I'm trying to basically do is I'm trying to rewrite this logarithm. I'm trying to rewrite this, and I want to actually try and define what u and v actually are, kind of an expression for u and v in terms of in terms of r and theta. Yeah. Okay, well this one's fairly easy. This one's fairly easy because I've got an e here, I've got an e here. I've got an I here, and I've got an I here. So it follows then the v here and the theta here are the same. So v is equal to theta. Okay, great. Okay, so in other words, v equals theta, this is just my argument. This is my argument of z. Yeah, because theta, if you remember, theta, this is z, this number here is z. Okay, it's moving, this like my origin on my Argand diagram, on my kind of complex plane, is moving from my origin to my point z. Okay, well, theta just defines the angle which I sweep out, okay, to get from the real axis to get to z. Yeah, you should have remembered that from the first part of this course. Yeah, so this is my argument of z. But notice that theta will just sweep out a circle. This complex number will just sweep out a circle. So I'll effectively just get a circle which is swept out. That's not a circle, but you get the idea. We'll get a circle which is swept out. So in other words, how many times, if I sweep out a full circle, what's my angle which I sweep out? Well, it's 2 theta, right? But I can keep going, you know, just because I sweep out a full circle, so if I go all the way around here and I end up back where I started, I can actually keep going. So I can keep going around the circle n times, okay, and we usually write that 2n pi. Okay, so in other words, theta plus 2n pi, so my angle, and then I can also keep going around the circle 2n pi, so I may have already gone around the circle 2n pi, or, you know, times already, and then I'm at theta, so that's kind of what's going on there. So actually my argument of z is defined as, theta plus 2n pi. Well, that's no good, because remember, I want v to be a function. I've said v up here should be a function. It's a function of z. Well, in order to be a function, it needs to be either many to one or one to one. At the moment, it's one to many. Because if you have a look, I've got this circle, and what this is basically saying is that this is real value, okay, but you can think of it as an x value if you like to think of x and y. So this is x and y. So one x value corresponds to more than one y value. That's no good. Because remember, with a function, I want to put one value in. So with a function, let's say y is equal to f of x. Okay, I want to put one value of x in, and I want to get one value of y out. Yeah, if I put one value of x in, if I get more than one value of y out, it's not a function. It's no good. Okay, because that kind of defies the point of a function. So in other words, I want to put one value in, and I want to only get one value out. So in other words, it has to be either 1 to 1, so one x value corresponds to one y value, or at the very worst, one x value more than one x value corresponds to the same y value. So in other words, if I just get rid of this second half of the circle, there's my y value that I get out if I put that value of x in, and I get that y value out. Well, I can also put this value of x in and get that same y value out. That's fine. Okay. So in other words, I only want half a circle. I can have the positive half, or I can also have the negative half. What's my angle going to be? Well, it's going to be between pi and minus pi. Yeah. So in other words, I want to define my theta as only being between pi and minus pi. Okay, and we're going to call that the principal argument, because it's the first thing that comes in a circle. If you like, if you start here on the x-axis and you sweep out half a circle, that's the first sort of set of points that you sweep out. You can carry on going, fine, but I just want to define it as the first set of points you sweep out. And likewise, if you go the negative way around the circle, you start here, you go the opposite way. It's just a principal argument. Yeah, it's the first set of points that you sweep out, and I'm going to denote that by capital arg. So the capital arg of z is just basically theta going from pi to pi, so minus pi to pi. So it can either go the negative way around the circle, or it can go the positive way around the circle. Yeah, so in other words, going anti-clockwise, or it goes positive clockwise, and basically it's only defining half of a circle. Yeah. So you still get all the points. But it just means that you can only go anti-clockwise, and you have to finish at this point on the x-axis. You have to finish on this point on the x-axis over here, or you can go the clockwise way around the circle. You still get the same points. It just means that basically you can only go from minus pi to pi. Right? Okay. So v is equal to the capital argument of z. It's capital A. Now look here. Okay, this one's slightly easier to define. I can rearrange this to get u, because remember, I've got v now, so now I want u, so same thing as I did before at this first part of the video. If I just take now the natural logarithm of r, okay, well, what's r? Remember, if I've got my complex number again, I've got my complex number starting from here to here, the r is just the radius, if you like. It's the length of this vector, okay? Well, the length of this vector can just be written as the modulus of z. Okay, so what I've effectively got is u is equal to the modulus of z. Yep, hopefully you get that. So what I've basically got is that the logarithm of z is, remember, u of z plus I times v of z. U, I said, was the natural logarithm of z. I said that up here, just said that just now. Okay, and then I've got plus I, and I've said that v, as I times v, and I've said that v is the argument, but it's the principal argument of z. Okay, and just to show that I'm looking at the principal logarithm, I can't define the logarithm of the whole circle. I have to kind of split the circle up, and I can't carry on going round. And just to show it is the principal, I use a capital logarithm here, just like I used a capital A for the argument. Okay, so that's looking pretty good. Okay, so I've basically I can show the left-hand side of my equation. Let's find it. Where are we? Here we go. I can show. Yeah, this is what I'm looking for. Sorry, this is what I'm looking for. I can show that left-hand side works if I use the principal logarithm. So now what I want to do is show that now the right-hand side gives me the same thing on the left-hand side. So in other words, the logarithm of e to the z will give me z again. Okay, so let's find my space. So what am I after again? I'm after the logarithm of e to the z will give me z. Okay, that's what I'm after now. And then if I've shown that, then I've shown that both sides work. Okay, well, remember that the left-hand side, which was e to the log of z, is equal to z if and only if this logarithm function is the principal logarithm. Principal logarithm, which remember was, I'll just write it down, it's up here, but natural logarithm of z plus I times the principal argument of z. Hopefully that's not quite gone off the page. Oh, I'll go away. Okay. Let's move over a little bit. There we go. So that's only true if we're looking at the principal logarithm. So now we've got to basically look at the principal logarithm here. So I'm going to let z equal, I'm just going to write it in equivalent form. Remember before we used r e to the I theta. I'm just now going to write z as x plus iy. Okay, that's just another way of writing z, and it works here. So remember, I can only use this if it's the principal logarithm. So I've got principal logarithm of e to the z. Because the left-hand side is only true if it's the principal logarithm, so therefore the right-hand side can only be true if it's the principal logarithm as well. So I'm just going to look at the principal logarithm now. Principal logarithm of e to the z. Well, what's z? What's z? So this is the principal logarithm of z, which is x plus iy, e to the z, which is x plus iy. Yeah, just making a substitution. And then just again using power laws, I can break this down into logarithm of e to the x times e to the iy. Okay, so what is the logarithm, principal logarithm of e to the x? How can I rewrite this? How can I rewrite this? Well, look up here. The principal logarithm of x, I haven't written that quite right. I keep joining it up. It's not, it's the principal logarithm of z, let's just make it really clear, is equal to the natural logarithm of my thing inside my bracket. So the principal logarithm of something is equal to the natural logarithm of something plus I times the principal argument of something. Well, my something now is e to the x times e to the iy. Okay, so this is ln e to the x times e to the iy plus I times the principal argument of my thing inside my bracket. So e to the x, e to the iy. Okay, well, remember before I wanted to find my principal logarithm of something, okay, as a real part plus an imaginary part. So in other words, a real function plus an imaginary part of the function. So if I want this now to be u of x, my ln x, to be u of x, maybe if I write it underneath there, v of z. If I want this now to be real, well, basically, I need to just ignore all the imaginary parts. Yeah, because I want this to be strictly real. In order to, because that's how I define my principal logarithm. It has to be a strictly real part plus a strictly imaginary part. So in order for this to be strictly real, I have to get rid of the imaginary parts, the thing which doesn't make it real. Okay, so basically, this is now equal to the ln of e to the x plus I times a similar kind of idea here. If I want this to be strictly imaginary, I have to get rid of the things which make it real. Because I can't consider it. If I'm in the imaginary plane, I can't consider anything which is real. So I get rid of e to the x, and I'm just left with the principal argument of e to the iy. Okay, so now I've basically defined my principal logarithm thing. Okay, so I've now defined basically the principal logarithm of e to the z. Okay, principal logarithm of e to the z So this is e to the z now. Yeah, because I've just taken this, and I've moved it down there. This is just considered for motivation, so you kind of don't need that anymore. So this is the principal logarithm of e to the z, because e to the x times e to the iy is e to the z, and that's equal to the natural logarithm of e to the x plus I times the principal argument of e to the iy. Okay, well, I can rewrite this natural logarithm of e to the x just how we rewrote it before. It was just x, yeah? Natural logarithm of e to the x, just x, yeah? Plus I times the argument of e to the iy. Okay, now the thing is, this works, but it's only for a very specific set of cases. It only works if y is a member of the interval going from minus pi to pi. Going from the interval from minus pi to pi. Yeah, not inclusive. So in other words, I can only consider y from going the positive way around the circle around the negative way around the circle. So it doesn't work for all values of z. So remember that z is equal to x plus iy. It doesn't work for all values of z. It's only a very specific case that this works for. So therefore, I can't say that in general, I can't say definitely that for in general, e to the z is equal to z. Okay, because it's not true. It's not true for all values of z. It's only true for some values of z. Yeah, because I've basically had to define y. So y can only basically be a member of these values. Yeah. Well, that's just a very specific case. So I have to basically say it's very specific. Okay. Now, kind of a small little thing. So a small little thing. It does work, but only for a very specific cases. So I can't say that for every single case. I can't say that in general. So in general, I can't say that my thing works. So I can't say that e to the log, this principal logarithm of z. It's bad enough that I had to use the principal logarithm here. Okay, but now I've basically shown that it's not true for every single case. It's not true for every single case. So I can't say it's true for every case. It works for some, but it doesn't work for every single case. Okay, so basically, I can look at this side here. So basically what I now need to look at is this as a function, this principal logarithm as a function. Now let's look at it. And in order for it to be a function, in order for it to be analytic, it needs to be differentiable wherever it's continuous. Okay, so if it's analytic, it needs to be continuous and differentiable. So wherever it's defined to be continuous, it also needs to be, so continuous is just it carries on. There's no discontinuities or anything like that. You know, it's a discontinuity down here. So get from here to here, it's like a jump or whatever. It just kind of carries on in one smooth function. It needs to be continuous and differentiable. So basically what we now need to ask is what is the derivative of the logarithm of z? So what is the derivative of the logarithm of z? Well, we can rewrite it as this. The function differentiated is a bit like f dash of x. Yeah. What is this? Well, let's say, log of z is just equal to ln z plus I times the argument of z. Yeah. So what's the derivative of this? Well, what's the derivative of this? Well, are you happy? Are you happy that that is just 1 over z? Yeah, the natural logarithm of z differentiated is just going to be the 1 over z. Yeah, that's just from calculus. That can be shown. But yeah, it's just equal to 1 over z. So hopefully you could realise that the derivative of logarithm of z is equal to 1 over z. But then what I'm basically doing is I'm taking what is the derivative of the argument, of I times the argument. Well, are you happy that the argument of z will just be equal to a number? It's just going to be equal to theta. It's just going to be equal to, say, like pi, or it's going to be equal to 2 pi, or it's just going to be basically some number. So what I'm basically saying is, what is the derivative of a number? It's a bit like saying, what's the derivative of 3? What's the derivative of 3 with respect to z? Well, it's obviously going to be 0. Yeah? So I've just got plus 0. So in other words, what I can now say is that the derivative with respect to z of the principal logarithm of z is just going to be equal to 1 over z. Okay? Don't worry too much about that if you don't get it. It's just kind of a small little part. The important thing is this thing, this idea here, that basically the left-hand side is only true and it's not true for the right-hand side.